Hi, this is Dr. Andrew Chrysler teaching EE 3340 electromagnetics at Idaho State University. In this video, I'm going to be discussing a classic problem derivation, which is the electric field due to a ring of charge, or the uniformly charged ring electric field. Now, on YouTube, you'll probably find many videos discussing this. In many textbooks, you're going to find this problem. Probably almost every physics or electromagnetics textbook has this problem. However, I'm going to discuss something in this video which I often don't see in the other solutions, which is from a vector perspective, why don't we have an r hat component? So most of these other videos or things that you look up, they're going to rely heavily on geometry and making clever observations and just kind of implying like, oh, you should just realize that the r stuff is going to cancel out. But from a vector perspective, if you try to set it up vector-wise, you're going to see in cylindrical coordinates, you're going to see, oh, there should be an r hat component, and when I integrate it, it's not zero. So, you know, what's going on here? Why doesn't this vector perspective give the correct result? And so this video is an attempt to make that clear. So I'm using the Ulaby textbook, and this in that textbook is example 4.4. So if you're using that textbook, you can follow along there. If not, I have a couple figures that you can check out. So in that textbook, and many of them, they set up the problem like this. You have a ring of charge, looks like this, and you want to find the electric field at some point at the center of the ring, some point up above it. Sometimes this ring is set on the other axis, sometimes not, but in this textbook, it's set up on the z-axis, and we want to find the electric field at some point P that's height h above that, and that h could be variable. Okay, so the familiar result, and this is what you'll find in all the derivations, is that of course there's only going to be a z hat component because, right, as it shows in this, you can see that clearly there's going to be a bunch of cancellations. But what happens when you actually try to set this up using vectors in that cylindrical coordinate system? Well, you're going to end up trying to do some integral, and you're going to be wondering, why isn't this a non-zero result? So let's take a look using the cookbook method that I teach using this class. So if you start out at the origin, setting up an origin for your coordinate system in your problem statement, we have an origin that's going to be right here at the center. And we have the ring that's radius b, and we're looking for the E field at point P that's h above. Now, step 2 is to write the vector rs. That's a vector from the origin to the source of the charge. That's the location of the charges that you want to find. So these are everywhere on this red ring. Step 3, write a vector from the origin to the point of interest. So that point of interest is your point P up here on your z-axis. So we've made it a vector from the origin to that point of interest. Now make a vector rsp, and you can find that by taking rp minus rs, and that's a vector that points from the source to the charge. From the source of charge to the point of interest. Now find the unit vector of that by doing this. Step 6, determine what your dq, what little bit are you going to integrate by, and in this case, it is a thin ring of charge, and so that is going to be a line integral. So we're going to have some rho L, and that is a line charge density, dot with a dl, and for this case, in the cylindrical coordinate system, our dl is going to be r d phi. So that line that we're integrating on is at some radius r around in that phi direction. And for our case, the radius is b, so we'll substitute r equals b. Now putting that all together, our dq and our integral is going to be rho L b d phi. Now we are able to get to this expression that we could integrate in order to find the electric field. Now we have this dE on the left side, and then on the right side we have everything that we just determined, our dq and our vectors rsp. Now when we put this together, we can see that based on the work we did, based on this vector-wise approach, we can see that there's an r hat term and a z hat term. Breaking it up a little bit, we can write it like this, and we can see that our integral is going to have two parts, one r hat, one z hat, and both of them we're integrating by d phi. Now, this is kind of weird, right? Because we just saw, right, if we were to back up here, we know that the classic result tells us there's only a z hat term. And we can easily see that if we were to do this integral, that it's not going to make sense. We're going to still have some r hat term. And so why does that happen? What can we do about it? And the answer is that this is not going to make sense for this reason, which is that you cannot easily integrate a variable vector. So when you're integrating around in that phi direction, what you're actually doing incorrectly is you're trying to add up all these r hats, which are actually not in the same direction. So as you try to perform this part of the integral, what's happening is that you are trying to add up something like r1 and r2, which are evaluated at different phis, phi1 and phi2, but you can't really do that easily. This is a variable vector. So if in order to get the correct result, you can go back into the Cartesian coordinates, and this will force these into x, y, and z forms so that you would get the correct result. So let's go ahead and do that. We'll convert this to Cartesian form. So this RSP hat vector, so the unit vector in that RSP direction, we can convert this to Cartesian coordinates. To do that, we'll write it out in a longer format where we can easily see the r, phi, and z terms, and we can see that the phi term is 0. So the RSP we should convert this into a x, y, z format, and from the cookbook or online you can find what the ax, ay, az terms should be. Now, knowing and realizing that the a phi term is 0, we can find ax, ay, and az quite easily and perform this coordinate system exchange. Now, from there, we have this RSP vector, which is in Cartesian coordinates x, y, and z. And what we can see now is that we have this dE term, but now we have, instead of r hat, we've been able to substitute it for the x hat and y hat terms. And I've left this with the phi terms since we are integrating by d phi for convenience, and also for something that we will see now, which is that when we integrate the d phi from 0 to 2 pi, that is going to be 0 for both this x term and this y term. So this is how, in the vector-wise format, this is how these actually end up canceling out. You can see this by performing this coordinate system transfer. So when we do this integral now, integrating the left-hand side and the right-hand side, and the right-hand side has this d phi, and we know because it's a ring that we want to integrate all the way around in the circle of that ring, right? We want to integrate all the way around from 0 all the way to 2 pi. We can see that that term is going to be 0 for the sine and the cosine version. And so this result that didn't make sense before, right, when we arrived here, we were wondering, well, what's the deal with this r hat term? Shouldn't that be gone? Well, we can see now that will be gone, in fact, and that we do only need to integrate the z hat term here. And doing that integral from phi equals 0 to 2 pi, and evaluating, we arrive at this final result. And in fact, this is only in the z hat direction, and we can see that this result is familiar. It is in fact identical to that result that's in the Ulubi textbook, and that you can also find in many other YouTube videos. And again, this would simplify even further this dielectric. If we were to do this in free space and set this equal to 1, it would be exactly identical to this Ulubi result. So hopefully this helps clear up how you can use this cookbook, how you can use vectors to do that integration. The integrals still work. I think it's a good idea to understand this from that integral perspective, and not simply rely on the geometry and hand waving away the idea that this is going to cancel, but actually seeing from the mathematics that it will cancel. So thank you, and I'll see you in the next video.